Thank you for joining me for the 10th episode of the Doc Talk with Liz podcast. This episode features Dr. Katie Galloway. Dr. Galloway is a professor of chemical engineering at MIT and runs the Galloway lab. Hello, everybody. Today, I am speaking with Dr. Katie Galloway, who is actually the PI of the lab that I do research with at MIT. So we're very excited to have her on today. Thank you so much for joining us, Dr. Galloway.
Yes, Lizzie, thank you so much for inviting me. I'm really delighted to get to share some of the story of my story in science and engineering and my enthusiasm for the work that we do in synthetic biology and using that into stem cell research. And so I'm delighted to get to talk with you today.
Absolutely. And thank you so much for being here. So I kind of just want to start off before we get into the stem cell research and synthetic biology sides of what you do. If we could start off talking about what actually led you to engineering in the first place, and then furthermore, how you ended up splitting off into chemical engineering rather than, biological engineering or all of those other things. So I'm really interested in hearing how your upbringing influenced you to go into this. I mean, were your parents engineers or your grandparents or anything like that?
Yeah, so let's see here. Growing up, I think that I always thought, so my mom is a physical therapist and my dad works in construction as a superintendent. So he was always designing things. My mom was always working with patients and with people. And I had relatives who were veterinarians. So I think I thought that those are things that I would probably do. I'd be like somewhere, if it was medical, I would probably be like taking care of horses, which is what I wanted to do. And I didn't necessarily see myself as a scientist, even though I really enjoyed science, all these science experiments and things, and different hands-on things we got to do as kids. We set up like secret chemistry labs in our closet, and my parents were very horrified about this when they found that nothing burned down. We were safe and fine, but yeah, I think that they realized like we need a positive outlet, for this creativity. As I did science fairs and things like that as a kid, but again, I had this affinity for science, didn't really know exactly what it was, did fairly well in school, but mostly I think that wasn't necessarily driven by any sort of like necessary talent or anything like that, just mostly actually being somewhat competitive. And I was also a soccer player and played fairly competitive soccer. And actually, I think that's sort of a lot of the motivation is just striving to be the best at things as much as possible. And then actually, I think my curiosity is something that took over later when I went to grad school. Before getting there though, when I was in high school, one of my science teachers kind of saw that I saw, I guess, maybe something that I didn't see, which is that I did have some talent for science. And I was like, well, why, you should look into chemistry, you should look into engineering, that these might be good for you. And at that point, I didn't know anybody who was an engineer. I didn't really know what engineering was. And I didn't see myself as a scientist, but I started looking into it and I was like, oh, well, engineering is basically solving problems with, scientific tools and then applying it to figure things out. And I said, oh, that's really interesting. Mm-hmm. And I think it was actually possibly a BASF commercial that really got me very excited, which maybe sounds funny. I actually think there's a lot of things in culture that shape us in interesting ways. And this is one time I can point to something, but it was a BASF commercial that was like, we don't make a lot of the products you buy. We make a lot of the products you buy better. And it was this idea that you could take chemistry to then apply and make these really interesting, engineering solutions. And I'm like, that's what I want to do. I'm not so interested in necessarily making this thing or that thing, but I'm interested in thinking about how do we make these things better? How do we make just things better with chemistry and engineer and solve problems? So that sounded very interesting. So that took me to a place where I was actually volunteering at a lab at UC Riverside. And in my senior year of high school, and learning how to do things that were really cool. It's kind of the beginning of synthetic biology back then, was just using some proteins, smacking things together and being like, can this thing act as a fusion protein? Yeah. And can we do interesting things like chelate mercury out of water that's contaminated with mercury and then pull down using these proteins? And I was like, this is super cool. And but even then, I still was like, well, I don't know if I love research. It's a lot of work. And, it's pretty intense. I think, at the time 17, like, I'm like, I kind of just want to go to the beach and hang out too with my friends. And that's what they're doing over the summer. And I was in a lab, which was a great opportunity. And I think that it also made me realize that, I had a little bit of growing up to do to be able to appreciate and value the experiences that were in front of me. It was wonderful and tremendous. It was also a lot of work. And I think that that's a normal place in terms of everyone's development. You eventually get to a place where certain types of work become easier because you've gained a little bit more, I don't know, maybe endurance is the right word.
Yes.
And so there's people out there who kind of find they're like, oh, I don't know, this seems pretty tedious and difficult. I think that can be true. I think research requires actually more persistence than anything, and focus. And I think that's actually something that is that develops over time for people, and especially is like a good sign of that you are maturing. I don't think it's something you're born with, or for most people, they're not born with a lot of it, and it varies across, time. And I think that's actually another thing that's really useful to think about in terms of people's scientific interest or engineering interest. Sometimes people think they're, that people who are scientists or engineers have a lot of talent, and maybe that's true a little bit, but I actually think it's much more about developing those things. Again, I don't think I'm someone who's necessarily extremely talented. I think I'm someone who's extremely curious, and then very tenacious in wanting to like figure things out and push myself to be better. And was very fortunate to be put in environments or surrounded by people who would help me to get better and to see things in ways and push me in ways that I even couldn't push myself. So those things combined, I feel like have made me a better scientist and an engineer than I ever would have been just on my own. And so kind of like always leading and trying to reach further, made a big difference. That I wasn't, in the beginning, I wasn't the scientist or engineer that I was going to be, that it's a process of becoming, and I'm kind of choosing and continuing to go on. And that, again, is more just a matter of tenacity and perseverance. And so for people who are considering that, it's like, if you want that, then, choose it, and then just keep convincing yourself that you want that. When you're discouraged and having people around you, because that's another thing. I think it's easy to be discouraged on hard paths. You need people, and people think about this all the time very easily. I think with sports is a good analogy. It's easy for discouragement to come in. The same thing happens in science and on any professional path, is you need people to encourage you along the way. And then you also need to find times to take breaks and to refresh. And I think this is especially timely as we're kind of heading to the end of a semester. I think, are you at the end of your semester or close there? You're probably ready for a break. You're probably ready for.
Yeah, we ended April 30th and started again May 12th for the summer semester. So I mean, not much of a break, but it was
my. Yes. So this is, I think, an important thing is, pushing yourself as hard as possible, but also then, to get better, but then also recognizing when you need to have that rest, weekly, yearly. Like there's times I think that you have to take for reflection, for rest, and for to be able to sustain the drive towards things that are important for us. Because there's times when you're going to really be cranking, and there's times you just need to like scale back, and things might be also, in your life, we're like, okay, we need to think about how much we can do at any given point. And for me, that's something that I really thought through with, I have 4 children, and sometimes it's time to crank, and sometimes it's time to just batten down the hatches and survive the storm. Yeah. And knowing what season you're in is really essential. Like, are you making progress, or are you just trying to like not lose ground? Right. And I think that varies for everybody based on things that are going on, and knowing what season that is always, again, a need for like reflection on one's own life. So, and it's good to have mentors who can sometimes be like, I don't know if now is the time to push. You might need something else. Or other times people, the inspiration where you're like, I don't feel like I can. And it's like, no, now's the time to push, dig in if you're right near that breakthrough point. So there's no one answer on what you should do at any given point in time. It's highly dynamic. And it really helps to have people, I think, around you to help give you some insight and to believe in you, and also then to pull you back and pick you up when you need that. So those are the things that I would say to people who are wanting to set out on any sort of rigorous journey, whether it's in science or somewhere else. You want good people around you to encourage you. Encouragement's really important for hard things.
Absolutely. That's also something interesting with needing to take rest, and how actually taking rest can actually give you more progress than continuously pushing. I think of it kind of like an example of when somebody, like the night before an exam, and you just want to stay up and cram, but actually, you know, sleeping would probably allow your brain to sort things out that you've already went through better. So it's kind of like you really want to push yourself, but sometimes there's somebody around you like, well, you'd probably better just to sleep at this point.
Yeah, no, I remember very vividly, like occasionally my dad coming in and it's like late at night or something, you know, 11 or getting towards 12 o'clock at night. What are you doing? Like, you need to go to bed. Like when I was studying in high school, and he's like, you know, you get to a certain point where you're getting negative returns on your time. And so you're not, I think of this as an engineer, it's like there's an optimal amount of time you can spend on something given whatever time you have. And if you're cutting into your sleep too much, you know, oftentimes you're not making any progress. You're actually just cannibalizing from your tomorrow.
Yeah.
And that's not a good thing. So you want to, there is this, I think, optimization type of process where you think of like, okay, I can only do up to this much and then I need to rest. So there's a limited window sometimes to work. And my mom used to say, actually, I think she still says this. She used to say it all the time. She's like, you got to make hay while the sun shines. And it was basically this idea of like, there's a limited time to work, and you need to work hard when that comes. And then because there's going to be a time when, you know, the nighttime comes, the sun's not shining, and you cannot work. So this is, I think, something that's been very much ingrained in my mind is, you know, you've got to take those opportunities, work hard when you can, because sometimes you won't get another one.
Right.
And things come up where you're like, I wanted to work hard at this time, but you know, other things happen. For sports, it's like I got an injury, or you know, working in lab, you know, some contaminations come up. You know, who knows what it is? Sometimes you just you know hit that thing, so you want to make the most of the opportunities when you have them.
Yeah.
But also know that some of the time is resting. So it's
absolutely. Yeah, that's definitely completely true, and obviously something that I'm still working on. I think a lot of people are still working on. So it's good to know that you know, there's always people out there that everybody's kind of struggles with that a little bit, maybe work-life balance, and also knowing when to take a break when you have all these people around you and you just want to keep working for them. But at some point, you know, it's like that. I've heard a saying before. It's like no, like make your bed in the morning or something like that. Like you need to take care of yourself before you can take care of other people, that kind of thing. I mean, I butchered the phrase right there, but it goes something like that.
I think of it as the air mask, you know, it's like secure your oxygen mask before you secure the mask around you.
Yep, that's a good one.
But yeah, I think that there's some utility there in making sure that, you know, you're good to go, so that you can keep being useful.
Right. Yeah, that's definitely an important thing to consider.
Yeah, so these are, I mean, important. I should say, I think that you highlighted, you're like, oh, I'm still figuring this out. So I would not say that anybody ever figures this out. I think what it is and how it's figured out like varies by degree, and then the challenges change too. So you're going to figure this out, I think, as a college student, for any given semester, for any given year. And then you'll move on to something new and you're like, okay, I'm figuring this out again. And so the skills and the thought processes that you develop now for even just figuring it out will serve you later, even if the exact schemes controlling that are different.
Yes.
It doesn't go away. But you'll get new challenges, so you don't get bored. It's not the same ones.
That's true. That is a good point, and something to look forward to, kind of, I guess.
Indeed.
I had another question from kind of what you just said. So, or what you were talking about previously with research and going into engineering and synthetic biology. So you are a chemical engineer, but you did a lot of synthetic biology research. So there's a lot of kind of intersections between synthetic biology and chemical engineering, or how does that work?
Yeah, so let me talk about that. So yeah, my background is chemical engineering. I was a chemical engineer undergrad at UC Berkeley, and I had like I think we got an emphasis in like biotechnology or something like that. And from the beginning, I was really interested in this idea that we could, I mean, one, the cells kind of like this is so the kind of the first wave of synthetic biology, or maybe somewhat precedes synthetic biology, was a lot of people in chemical engineering working on metabolic engineering. And thinking about how do we maximize flux through a pathway And we've thought about this as chemical engineers in the chemical space. And then this is more thinking about, oh, the cell as that reactor and optimizing reactions through that. And so that was kind of there was already that sort of framework around the year 2000 when people started asking questions. Well, can we build biology from the bottom up and do simple things like build a toy circuit? And a lot of that comes, that language even comes from the electrical engineering. And what was happening around that time was you had engineers who were just becoming really fascinated with biology and with the idea of building and understanding life, who are coming into the biological space and also saying, oh, we want to make this more like an engineering discipline and more quantitative, so that we can play around in here with our, mathematical tools. And that was, I think, this really fruitful time when synthetic biology was born. You had Michael Olowitz's Repressolator was published that year. You have the Jim Collins' Toggle Switch. These are two landmark papers in synthetic biology that really launched the field. And gosh, now that's like 21 years ago. So, but it's still a relatively new field. And at that time, I was completely unaware of those papers. I was just graduating high school in like 2001, but I had been playing with like fusion proteins. And when I went to college, I was kind of interested in like protein still and protein purification and things like that. I was still really unaware of what synthetic biology was. So I get to grad school and I started working in Christina Smolke's lab, and I was really fascinated. She was building these genetic control systems or ways of regulating gene expression using RNA. And to me, that was even more fascinating. I still love RNA. RNA is fascinating in terms of what it does, especially in higher organisms. The amount of regulation that we think is associated with RNA is just really, really amazing. So thinking about this, it's like, oh, it's not just the genes, it's not just using some proteins together. It's actually then these control systems that are then making cells behave in different ways. And probably the most different ways in which we kind of traditionally think about cells behaving is that you have completely different cell types when you get to these to multicellular organisms. So obviously we start as a single cell, which when we're pretty identical at that point. Your cell, right? You have one cell, and over time we go into this highly branched state where you have very, very different cell types, organs, and those are all essentially genetically identical. Although there's some asterisks that we should put there. Essentially genetically identical, but obviously running very different genetic, ensembles of those genetic programs to have different behaviors. And again, thinking about that, I'm like, wow, well, that's fascinating. If we can control gene expression, then we can move anywhere on the landscape of cell identity. You can go from being an eye cell to a brain cell to a heart cell to whatever. Essentially, you have all potential opportunities for plasticity in theory if you can control gene expression. And that's the question, is like, if you can control gene expression. And so that's what I wanted to do.
Right. Absolutely. And I'm also wondering, so you're saying that we can start off with a cell and then kind of based off gene expression, change it to have different functions. How is that possible? I mean, is that because of something with DNA, or how does that kind of work?
Interesting. So it's maybe a more deep theoretical question or a philosophical question. Well, why is it possible? So I should say, now there are different genomes that you're working with, right? So when I say you're going to change a cell type, you're not going to change a bacteria into a yeast, and you're not going to change a yeast into a human or something like this. You're going to stay within your species. Putatively, you might make some chimeras or something like that, which people do with human and mice and things like that. But so in theory, you can change. So the field of stem cell biology really, I think, got going in an explosive way around 2006, 2007 with the discovery of iPSC reprogramming. And this was essentially one of the biggest or most dramatic examples of being able to change cell identity through gene expression, in that you could take adult human fibroblasts, cells that were fully differentiated somatic cells, and then use gene expression, this overexpression of these Yamanaka factors, KLF4, OCT4, SOX2, and MYC, and basically then massively increase them and then make induced pluripotent stem cells, which are, as far as we can tell, nearly identical to embryonic stem cells, meaning they have this amazing potential to differentiate into many different cells. And that is, again, so how is that possible? is that the question you wanted me to get to? In theory, that's because all of the genetic, the transcriptional networks are in the cell. And if you could just activate them, then you could move from a transcriptional state that is then characteristic of a fibroblast. And therefore that transcriptional state at the RNA level then radiates out into the proteome and also into the changes in the epigenome. Although there's some questions about like what's feeding back into what, but we'll pretend that that's simple. But if you can change that transcriptional state, in theory, you can move then to some new state, in this case, dramatically to an iPSC, which then has potential that this fibroblast never would have had. Like the fibroblast is never going to turn into a neuron, as far as we can tell, without some serious interventions. But clearly, with just changing expression of these factors, you could get some cells, not all, some cells to be able to transition. And maybe that's the thing that I missed when I was so curious about these this process. I was working with yeast at the time when these discoveries were made, and I was like, oh wow, you can reprogram cells just by changing gene expression. And I was trying to control cell fate in the context of yeast by controlling their MAP kinase pathways. Little known to me is like it was only like a fractional percentage of the cells that obeyed these programs. And subsequently, in my postdoc work, I wanted to ask the question, well, why? Why are some of the cells actually able to reprogram, and then why are some refractory? And it has something to do with some of the somewhat operating principles of the cell, that they are inherently built to be stable and resist these transitions, which is a good thing. It's probably why we are able to resist cancer and live relatively long lifespans. Although, and also have this regenerative capacity and also neurological capacity that we have. All of those things have to be balanced for us to be us. And it's a non-trivial thing, I think. Yeah, so it's quite remarkable that so this reprogramming process works. And so I was drawn and fascinated to that. So that took me to my journey into stem cell and to understanding how do cells actually change identity. And now my lab works on understanding sort of the principles by which cells are able to transition, and then also specifically then thinking about how do we optimize gene circuits then to function if we want to regulate cell behaviors, and specifically doing that in primary cells. This is sort of the next wave of what I think this is the next wave of synthetic biology, as we started in yeast and bacteria, and increasingly are expanding to mammalian cells, and specifically then looking to tackle challenges in primary cells, which remain very difficult to engineer with predictable behaviors. And I think that's just because we don't understand, not that we don't know how to try to basically design circuits, but we don't know how to design circuits necessarily that work in the context of a primary cell.
Right.
And so that's what I'm excited to be doing, and a lot of people in my lab are working on. So
yes, absolutely. And so you guys are working with stem cells, like you said, and gene expression and changing, like kind of controlling cell fate with genetic circuits. So I'm curious because you guys reprogram neurons to neurons, well, right now, and then like working on other cell types. But how do you actually control the transcriptional machinery to be able to change it so that it expresses to be able to go to a neuron?
Interesting. Okay, so a couple of questions wrapped up in there, I think.
Yes.
That's
a big question.
So just kind of the mechanism of what we do normally. So we'll have our test bed system is normally mouse embryonic fibroblasts that we will plate on a 2D culture. We will then prepare viruses that have that will allow us to overexpress these transcription factors that activate neuronal, or specifically actually motor neuron gene regulatory networks. And so when those the expression of those factors are induced, it then triggers, we think, then the activation of all of these different gene regulatory networks to drive cells from being a fibroblast to being a neuron. And that process actually takes about 2 weeks in mice. And for humans, it takes about 35 days. So yeah, and it's still pretty inefficient in humans. That's another thing we'd like to try and change. The mouse system works pretty well. the human system still has some limitations in terms of being able to really robustly and easily generate motor neurons. And so that's what the process kind of looks like. Additionally, we apply some different genetic interventions in addition to these transcription factors that allow the cells to rapidly proliferate and transcribe at high rates. And that seems to be a necessary criteria to get really efficient reprogramming and mature cell types. And so that actually involves then the induction of these oncogenes, which is really interesting. So it seems like the balance between plasticity, development, and oncogenesis is all very delicately wrapped around this sort of, I don't know, it's an almost intermediate state where the cell has this high amount of plasticity. It can move in many different directions, but most cells don't stay in that high plasticity state, and that keeps us, I think, somewhat stable in our cell identities and able to ward off most forms of cancer.
Right.
In the first part of this podcast interview, we learned that as an engineer, Dr. Galloway is interested in looking at how things can be improved rather than just looking at making things from scratch. Dr. Galloway says that being a great scientist and engineer develops through curiosity, collaboration, and hard work, not just talent. And going on hard paths, it is important to find people who will support and encourage you and to find time to rest and recharge. Dr. Galloway is interested in cell fate transitions. By controlling transcriptional networks, a cell can be changed into a different cell, such as a mouse embryonic fibroblast to an induced motor neuron. Cells can undergo transitions into other cells because all of the transcriptional networks for cell identity are in each cell. And to reprogram stem cells to neurons, they plate mess on a 2D culture. Viruses are prepared that overexpress transcription factors to activate neuronal gene regulatory networks. And activation of these drives cells to become neurons.
Right. And so you guys are engineers. So how do you, I feel like there's kind of a thing with engineering where everybody's like math. So I'm wondering how.
Oh, yes. So where does the math feature? So I think that we are trying to, always increase the quantitative nature of what we're doing, because there's a lot. I think even a lot you can discover just by asking, even are you on the order of magnitude of that you would expect for different things in biology. And the challenge right now, I think, in biological systems is oftentimes we can't measure things accurately enough. Like our models are far more like are overspecified with respect to what we can actually measure in a biological system. So the rate limiting step then in building better models is actually even being able to extract information from our systems. You can do a lot if you, even with very simple ODE modeling. And so this is sort of bread and butter of synthetic biology, is using ODE models to then build gene networks and models of synthetic circuits, and then applying different perturbations to ask the question, okay, something simple like I have a toggle switch, and now I'm going to increase the degradation rate of one of my proteins. Like, how is that going to affect the overall system?
Right.
So this is a type of modeling technique, and then you can actually go in there and then apply different perturbations. You could add in some sort of small molecule that could increase or decrease the degradation rate and ask, okay, are my predictions met? And if not, then are we missing something in our model? That's the most exciting thing. Everyone's like happy when they have a model that meets what they are trying to model. That's great. But of course, we learn more when the models don't match. We have to go back to the drawing board and be like, I don't think that this works.
Right.
There's something we're still missing, and what is it? So that I think is kind of the fun, the puzzling part about different things. Is that, and then sometimes we also have to figure out, okay, well, we actually, the most common thing is actually that we have multiple models that fit. And then the real question is, well, which one's the true model, and how do we even design an experiment that could tell us? Because the predictions within certain experiments are going to be identical. There's no way of disambiguating which one's important. And then, so I think that the scientific side of it for me, which is I think something I've developed more recently, is then thinking about these experiments. We're like, oh, I have the perfect control, the perfect experiment to like then figure out which one of these is actually going to work.
Right.
Which is the true mechanism, which sometimes you can do engineering apart from understanding the mechanism. You can say, well, this is phenomenologically what we're seeing. You have a black box essentially, and you're like, I push on this side and this is what comes out. And then I build a transfer function. It's like I push like this, and then this is what it maps like. And honestly, the details I don't need to know. I just need to know input, output, and then I go.
Yep.
But of course, sometimes, if you don't know the mechanism, that can get you into trouble. But it's remarkable how much you can do even with these black box models.
Yes.
So,
definitely. And actually, interesting fact, just for anybody listening in, maybe Dr. Galloway, I think you know this, but maybe it's a fun fact for you too. Actually, the way that I ended up meeting you was through doing research on ODEs and then finding the gene expression ODE on your webpage and then I went to your lab page and I was like, oh, this is awesome. Oh my goodness. And so I messaged you and you're like, sure, you can join us for the fall. And
this is actually I think this is a fun story for a couple reasons. So all of the modeling notes that that you've gotten to see were given to me by some friends of mine who are grad students at Overlap at Caltech, and it was actually only because of COVID that shut down our, the entire, institute last year, that I actually was so intent on developing these modeling tutorials, because all of our undergrads, our UROPs, had to immediately switch from this wet lab project that they were working on to modeling. And it was especially important for one of our seniors who had credits tied to this. I'm like, we have to figure out a way for him to finish up his units and make sure he can graduate. And so I was like, oh, I don't have any modeling tutorials together, but I reached out to Elisa Franco and Mary Dunlap and was like, do you have anything? And they shared these notes with me, and I was like, okay, I'll put them together. And then I was just going to send them out. And I was like, no, it's nicer to see them kind of written up as like a blog. And so I put them up there, and I'm thinking the only people who'd ever see them would be my UROPs. And it was so delightful. I was like, oh, someone actually found these modeling notes. Like, what are the odds? And used them and found them useful. And now many people have, more people I think have seen them. And we're trying to actually develop this into, a tutorial that actually will be running this summer with some of our UROPs. Yeah, so we're having another cohort of students going through the UROP training program, which we did last fall. And then there will be another group of students, some of who overlap, doing the ODE modeling. And that all happened because of COVID. So there's always a silver lining. I would not have put those together as rapidly and put them online if we hadn't been shut down by COVID. And I'm guessing you wouldn't have been looking for them because you wouldn't have had to do as much modeling for your iGEM project, correct?
So, exactly, because I would have been in the lab doing wet lab work, getting data from that, and just using like whatever techniques I currently had. So yeah, that's
So we think about a lot of the things that were kind of destroyed by COVID, but it's amazing to see some of the things that were birthed out of that and the good things that came out of it. So it's anyway, that's why I like that story.
Absolutely, yes, for sure. And so we kind of discussed your current research and what kind of led you here to MIT and the stuff that you do now and how math is integrated with all of that. And so now I'm wondering, you said that you have 4 kids. So yes. what do you like to do in your free time, if you're not at work? Hanging out with your kids or alone time or I don't know.
It is really fun to hang out with kids. Like for them, outdoor time is really good. Like just doing things like biking, going to the park. We'll come into Cambridge and like walk around the Charles. You can actually see this behind me. And we'll like walk around. There's a little park at the promenade across the way, and do things like that. It's been a weird year though too. Like we moved to Boston less than 2 years ago. Yeah. And a good portion of it's been kind of shut down. So we don't do too many activities right now, although things are about to change. We used to like to go to I really like the Science Museum, or the Museum of Science, which is really neat. Apart from that, if it's just for me kind of on my own, I like to run. So mostly for me, that's just stress relief. And being able to also stay a little bit in shape, but mostly I think it's actually to deal with just a lot of the energy of running a lab. And then what else? So additionally, I mean, hanging with my husband, we try to like find time to do that in between all of these different bits. And yeah, so there's not a lot of free time available for a lot of extra things, but finding times to relax and enjoy is really important.
Right. Yeah. Right. Absolutely. That's definitely, I mean, that's kind of a perk of also doing something that you really love, is that even if there's not tons of free time, you know, you can still spend time with people that you love in your free time, but you really love what you do. So it's not like you're at work and like, oh, I want to be done, I hate this so much. It's like,
no, I mean, that is actually, I do really love that. I really love my job. I really like, especially the opportunity. I feel like it's, being in academics, it's a very creative space. You have a lot of freedom to do creative and interesting things. So yeah, that is I think really the best part. The worst part is any sort of bureaucracy, like paperwork. I'm always like, oh no, a form. What is this? Yep. But otherwise, it's really quite wonderful to get to do that, and to interact also with students who are in the process of like coming up with creative ideas. I think the most fun is always like when you communicate an idea to somebody and then they mishear it, but they mishear it in a really cool and creative way, and you're like, I never would have thought to do it that way. Yep. That sounds very interesting. Let's try that. Yep. And so there's a lot of fun, I think, and then people coming up with creative, ideas that are completely like, oh wow, it's way beyond what I would have, imagined, and it's just a very, I think, fertile ground for thinking about new ideas. So I love it for that reason.
Right. Absolutely. Absolutely, for sure. And so you've kind of walked us through again what you do and all of that. Now, maybe there are people that are saying, well, this sounds really interesting and they'd be interested in going into it in the future. Do you have any tips for them now for what they should do or start looking into?
I guess it depends on the stage. Do you want to give me like an idea of like
it could be like anywhere from high school to college, maybe?
So I would do so whatever math classes you can. So I guess from an academic standpoint, like take the hardest classes you can. You won't be sorry if you do. No one's ever gonna be like, oh, I took too much math. Like it'll be useful for you. I would also say, so it was not common when I was in high school or even in college. Well, maybe in college, but definitely not in high school to take any sort of CS classes or programming languages. So I arrived at college without any programming experience, which I think is probably very unusual these days. So I wish I had a little bit better background in that, because it would have been very helpful. And so I think that maxing out on a lot of these, like learning how to do things, especially in high school. The thing about, if you're in high school, your instructors care a little bit more about you learning. Not saying that your college instructors don't, right? But it's not the same level of nurturing,
right?
So it backs out early, because people are going to be more invested in your success,
right?
I think. And then just to stay curious is really important, and look for those opportunities and follow up on that. Additionally, if you can get research opportunities, I would do that. There are both paid opportunities and there are unpaid opportunities. I can say opportunities, but really getting experience is your most important thing. So I worked at UC Riverside as just a volunteer when I was in high school. And that experience was just so important to me in terms of like learning what the field was about, learning what people were doing, learning how to do research. And so I wasn't, for like at least the first 6 months, I was just volunteering my time. And I wasn't that useful. I think I washed glassware occasionally. But eventually I became useful enough that I was trained, and they started paying me. So for like the last 6 months, I was, making about what you'd make at Quiznos. Per hour. But hey, you know what? That's better than nothing.
Right.
And I really got to learn a lot from it. But if you can afford to just do an unpaid internship, that will pay a lot of dividends later. I know not everyone can afford to do that. And sometimes there are paid opportunities, especially if you're in high school. But just volunteering to show up, most times people are like, oh, okay, that's great. Now they have to train you, so there's a bit of an investment. They're going to want to know you're there for a little bit. There's a bit of commitment. Right. But I think that's the best advice I could give somebody. Just get some experience, try to plug in, figure out where your interests are, and and look for good mentors too, people who are willing to commit to teaching you, not just, that they want you to learn things is valuable.
Yep, definitely. And that's actually one of the reasons why I'm really thankful that I found your guys' lab, because I feel like I have really good mentors. Like when Adam meets with me, I might say something crazy and he's like, let's walk through this real quick again, and that kind of thing. He'll just like walk me through it and kind of teach me it. So that's, I definitely think that I'm very fortunate that I was able to, like, even through COVID, like you said, the silver lining is I was able to find people, even if it was remote, that were willing to kind of invest in me a little bit more, even though.
Yes. This is like, again, it's funny because like I don't know that we would have thought about doing like, oh, I don't know, a remote thing, it might be too difficult, we might not be able to manage it. Now it's like, this is a totally doable thing. We could there's a lot of things we can do. So I'm glad that that's been a really positive experience. I've been so proud of the graduate students in my lab and the mentoring that they've committed to doing, because they want to see you guys succeed, and they want people to be excited about research. And also they recognize like, wow, all of these students who would have been trained in lab last year, what are they going to do? Like, if we don't offer some way of teaching them how to do research digitally, like it's, virtually, there's going to be like a lost generation. So they were just like, no, there's not going to be a lost generation. We're going to make sure we fill the gap.
Yes.
And that, I don't know, I'm just extremely proud of them. So yeah, and I'm glad that, and you too, the persistence that you've had, Lizzie, and continuously showing up to group meeting, continuously showing up for all these things, is tremendous. So way to go.
Thank you.
Yeah.
So now going off of this, we've talked about your journey through engineering and then tips for other people. And now I'm wondering, who were your role models for going into engineering and like even now being like a professor and a researcher?
Okay. Interesting. So it's funny because you sent me this question about role models and I was like, I don't know who my role models were. Growing up, honestly, my role models were like all people in sports. So I'm like, when I was a kid, it was Julie Foudy. She was on the women's national soccer team.
Yeah.
And actually Gabriella Reese, who was a professional volleyball player. And I just really respected the tenacity with which they approached their sport and, the excellence with which they did it. And so like, to me, that was very inspiring, just like persevere, continue, work hard. And I think I brought that to both sports and also then my academics. It was just the mindset. And then trying to think about role models in I guess maybe now is easier. I think this is the other thing is I think about, do I have any, I don't know if I have any one specific role model at any one point, but there's things that I admire about people that I'm like, I want to be like that person is. And maybe I should say, actually thinking more about sports, is like Simone Biles.
Yeah.
But I also really admire what she said. Someone asked her if she's like the next, I don't know, Michael Phelps. And she was like, no, I'm the one and only Simone Biles.
Right.
And I think that that's also some ways how I think about role models too. When I look at people, I'm like, I want to try to aspire to be like them, but also to be like them as myself.
Right.
And to think about what are they doing well? And then how do I authentically integrate that into who I am? Because I'm not going to be them. I'm never going to be them. Like, I'm me. And how do I though adopt the excellence that I see in them in a way in which is me, but also I guess I anchor that in thinking about how I think one thing for me that's important is as a role or as a mentor, as someone who's leading a lab, as a parent, like thinking about how is that also life-giving and looking at role models, like how do they bring life to situations, how do they lift other people up? So one of my role models is in this department, Chris Prather, who's been a professor here and someone who, when you talk with her, she is just someone who can give you great wisdom, advice, and not going to tell you things that you want to hear, but is also just one of those uplifting people, encouraging. And so for me, I seek to emulate just the joy and the clarity, the persistence, and also just the honesty. I think that she brings to different things. Like she has a no nonsense approach, but is also bounded with joy. And so you feel like you're dealing with someone who's just extremely authentic.
Yeah.
And I really admire that. And she has many admirers she's not on Twitter, but she has a Twitter fan club. I keep telling her, you need to get on Twitter, Chris, because there's so many people that say fantastic things about you.
Yeah.
And but she's too focused on getting things done. She's actually the executive officer for our department, and so she's a very busy woman. And she balances all that with, she also has 2 kids.
Wow.
And, so she's a tremendous role model. And then also our department head is just Paula Hammond is another really amazing role model. She's been leading our department through just a very tremendously challenging year on so many fronts. And brings so much grace and poise and just wisdom to things. I often think about like her example as in terms of leadership, and how do you lead groups, and how do you also make an inclusive and respectful place where people can be different, but also recognizing that sometimes those differences also need to be mediated through compassion for others, and this authenticity. And it's so much, I think, sometimes a bit imbalanced, because what if your authentic self is a jerk? It's like, well, we want you, like, no, you can't be that authentic. Like, I mean, you want your authentic self to then become the better version of your authentic self, because your authentic self is just awful to everyone. So there's there is a process of, like, leading groups with people in a way in which you think about how do you deal with conflict too. And this year has been, I think, a year of enormous challenges, especially with the unrest that we've had in the last year in the wake of the murder of George Floyd. And I think there's a lot of things that we've had to, emotionally process through, intellectually process through, and think about how do we make changes that are at the institution level, at the national level. And then how do we also allow space and time for everyone who needs to grieve, process, and move through these different things in their own time windows. This is not a trivial thing, but I've been really admired the way in which actually both Chris and Paula have really been leaders, I think, in helping us get through these different things, and as a department, be inclusive. So that's, to me, anyway, those are some of my role models. I'm trying to think if there's anybody else I really admire. So in synthetic biology, also I really admire. So my advisor is Christina Smolke, and she was a tremendous leader and just very creative, persistent, and a great mentor. Someone who always gave great feedback, especially on editing documents. I learned so much through that process, and she was just very meticulous. And again, that's one of the things that I'm trying to aspire to as a mentor, like giving feedback so people can learn through their writing. One of the most important modes, I think, of communication that we have as scholars is you're going to have to write. And then complementing that is then also building like really beautiful figures. I really admire the Elowitz lab, so Michael Elowitz, like he puts together the most beautiful figures. And then also in conjunction, another synthetic biology lab, Wendell Lim, like he puts together beautiful scientific stories that are then also wrapped with these beautiful images, so that you can really understand the science and the engineering very quickly. So those are people that I admire for that reason. And I mean, and for many other reasons as well, but those things stick out in my mind when I think of like who I want to emulate. I'm like, I really like how they do these particular things. And so those are, I guess, some of the role models that I have right now. I could probably think of many, many more. There's many people who I admire for various different reasons. These are the ones that come to mind right now.
Yes, absolutely. I definitely get that. I mean, choosing a role model, I mean, obviously I would say my parents are my role models, but like going deeper into like, scientific role models, sports role models, and then just like life role models, but all of those things kind of can intersect in different ways, just like what you were saying. So that's definitely something that's tricky to do, but good to find people to model certain parts of your life after. Seem to have it figured out.
Well, I mean, I guess I should say this, like, well, one thing is the ultimate role model is what, at least for me, is Jesus Christ. And the one thing they said in the Bible about him is like, he did all things well. And I'm like, he did all things well? Oh man. Like, I don't know. That's a very high standard to achieve. It's a very high standard to achieve. And so in some ways, and it's also a bit, it's the goal, but it's also, you have to be like, well, but how do I do that? And so that's why I think it's also useful to have people here where you're like, oh, they are doing this thing well. Now let me understand how they're doing it well so that I can figure out how I can do it well. So reverse engineer that. But at least for me, Jesus Christ is also the ultimate role model.
I don't even know how I would have forgotten to mention that. That's so true. Like, who's your
It's one of those things that it's hard to though also articulate. I mean, there's a huge campaign, I think, during the 2000s or something that, you know, what would Jesus do? I think answering that question is actually very difficult because Jesus was a very specific person living at a very specific time in a very specific context.
Yep.
And, you know, he didn't have an iPhone. So
right.
it's some of these questions become a little bit, the answers become silly because, you know, it's like, what would Jesus do if he was in your situation might be a more apt way of saying it.
Right.
But anyway, I think that this is, you know, why we have, you know, role models in our current day is to try and understand what does it mean to do things well. And then also what does it mean to do things well as you, not necessarily as someone else. And figuring out what that is, I think is, you know, a non-trivial process of self-discovery.
Yep, definitely. I fully agree with that. And I also just want to thank you so much for coming on today and being willing to talk about your experiences and offering so many really valuable pieces of advice. I feel like every time I talk with you, I just learn more things and I'm just like, that's really good. I need to write that down and like look through all of these. So thank you.
Well, now you have it recorded, right?
That's
so
right. Yes. Perfect.
Delighted. Yeah, Lizzie, thank you so much. It's really fun to share this journey with you just through, you know, conversation and you know, it's been a privilege to have you in the lab. Well, we'll hope to have you in the lab physically, but virtually in the lab and contributing in many ways, especially to, you know, the life of our discussion through group meeting and through all of the different ways we interact. So yeah, I think that this has been a huge privilege. So thank you very much for this conversation and your contribution to the lab.
Well, absolutely. Absolutely. And have a really nice day. So thank you.
Yeah, absolutely. All right. Thanks, Lizzie.
In the final part of this podcast interview, we discussed that in synthetic biology, many models can work, but the tricky part is figuring out which model is the true one. In her free time, Dr. Galloway likes to run and enjoys taking her kids biking or to walk around the Charles River. As an academic, there's a lot of space for Dr. Galloway to do creative and interesting projects and interact with students. Dr. Galloway encourages students to challenge themselves with their classes, learn how to code, remain curious, and to look for research opportunities. And lastly, Dr. Galloway mentions that it's important to find what it means to do things well, but to do those things well as yourself. Aspire to be like your role models, but to be like your role models as yourself.